anything here, but I'll just make it simple by putting 0 there. Okay, so this is a heat equation, slightly more complicated than what we've been doing before because simply of this one. So let's see why that becomes complicated. But before I explain, let me try to explain the physical meaning of this. Okay. So first we have a one-dimensional rod, insulated, and the left part is touching ice so that it's always kept at 0 degrees Celsius. The right side is exposed to a 20 degree Celsius room. So 20 degrees is about room temperature, so there's a room temperature it's exposed to here. And initially, the temperature here is 0 all the way around. Now, I want you to imagine what the solution might look like if this is the case. So, at time t equals to 0, you're going to get 0 to 3 as 0. And then, in a split second, this 20 degrees Celsius will make the right side temperature go up, right? So, like t equals to 0.1, suddenly it's going to go like that. Here's 20. Right? Something like that. Okay? It's going to go up. And then, sorry, I guess it's hard to see. T equals to 0.1, and let's say this is 20 degrees Celsius. The right side becomes 20, and then the other parts will speed up. And I just made up 0.1. I don't know what time, so some time. And then when you let time evolve for infinity, this will reach a steady state, right? Now, who can tell me what the graph of the steady state temperature will look like? Can you imagine what the temperature will look like?
Something straight.
It'll be a straight line from 0 to 20, right? So from 3, it'll be 20. It'll be a straight line. Because this is always kept at 20, this is always kept at 0, and there won't be any more change of heat or change of temperature. It will always be like this, with time t going to infinity. Okay? And having this intuition will really help you in understanding what's going on. If you don't have the intuition, then you may be able to follow the solution, but you're not really learning. Okay, so that's the idea. Now let's actually try to think about what makes this hard. So there's a fine point which I didn't explain carefully last time because of lack of time. But here's something I want you to think about. ut equals to 4uxx is a linear PDE. And actually linear homogeneous PDE. And by linear, what does that mean? If you have two solutions, any linear combination of the two solutions will again be a solution. That's what linear means. Okay? You know what linear combination means? You take one multiple, another multiple, and you add them together, right? So let's say, so let's just say, if V, W are two solutions, i.e. that Vt equals to 4Vxx. So V u, v, and w, they are all functions of t, x and t. Okay, so when I write v, I really am thinking of v as a function of x and t. Okay, so if you take v and differentiate by t, it's the same thing as 4 times v, and you do a second derivative with respect to x, and also that's true for w. Then saying that it's linear, that's the important part. Saying that it's linear means that if I take any multiple of v and any multiple of w, where a and b are constants, these are not functions. Hopefully it's not going to confuse you. So v and w are functions of x and t, and a and b are constants. If you take this and you take the derivative with respect to t, then because derivative is a linear operator, taking the derivative is the same thing as taking the derivative so taking the derivative of the first and then taking the derivative of the second, and any constant multiple comes out, right? And then these separately, because we have these identities, we know that this is a times 4vxx plus b times 4wxx. So that if you factor the 4 out and write it as avxx plus b times wxx, then this can again be written as 4 times AV plus BWXX. So what is this? This is the heat equation, right? So any two linear combinations, if you have any two solutions, their linear combinations will again be a solution. Now compare with this other one. If you have U0t equal to 0, is a linear condition. And it's the same thing. Again, if v of 0t is 0 and w of 0t is 0, then v plus w, if you evaluate this as 0 times t, that's the same thing as v of 0t plus w of 0t, so it's going to be 0. Okay? And again, you should also check whether if you put a and b there, it's still the same thing. It's still the same thing. Okay? So now let's go back to this other condition, u of 3t equals to 20. Now is this a linear condition? What happens if v of 3t is 20 and w of 3t is 20? What happens? What condition does v plus w evaluated at 3t give you?
40.
It'll give you 40, right? Because v of 3t is 20, w of 3t is 20 again, so it's going to be 40. So that's not equal to 20. So this is not linear. Now, why is linearity desired? Well, we desire them because, at least for the previous solutions, it allowed us to build more complex solutions from simple ones. So remember how we did it when this was 0. We first did that separation of variables. Separation of variables, you say uxt equals to x of x and t of t, and then you ended up saying that, this one is like e to the negative lambda, it's just 4 times n squared pi squared over 9t, and you find that the x of t is sine of n pi over 3t, so 3x. And once you find this one solution, then you can just take linear combination of all these because linear combinations are again solutions. So we are able to build from these simple ones obtained through separation of variables, and we took linear combinations of them to build a solution that had some complicated initial condition, right? So that's what makes us desire such a linearity here. But this breaks that linearity. So that's the thing that we're not so comfortable with. Okay? So that means we need to approach this in a different way. Everything. Let's come back to this. So here's the idea to solve this. You want to change this into the previous type of question. How? Well, think of U as V plus W, where Vt is equal to 4 times Vxx, right. And then V of 0t is 0, and V of 3t is 20. Okay, so it satisfies these two. Question. What equations does W satisfy? Okay, so let's try to answer this. Now, if U and V both satisfy the heat equation, is it true that W still satisfies the heat equation? Do you agree? Don't know? What is W? W is U minus V, right? U minus V is a linear combination of U and V. W is equal to U minus V, and that's 1 times U plus negative 1 times V. So it is indeed something times U plus something times V. And we know that if two functions satisfy the heat equation, their linear combination satisfies the heat equation as well. Right? You're getting this? Okay. All right. So we know that Wt is equal to Wxx. Okay. Now, what about W of 0t? Again, W of 0t would be U of 0t minus V of 0t, right? It's simply that W is U minus V, so if you evaluate W as 0t, you also have to evaluate U and V as 0t. What is U of 0t?
0.
0, it's given here. U of 0t is 0, right? What's V of 0t?
0.
Okay. What's W of 3t?
20.
No, it's U of 3t minus V of 3t, right? What's U of 3t? 20. What's V of 3t? So what's W of 3t?
0.
0. 20 minus 20 is 0, right? Okay. And this is a good thing because you know that Wt equals 4Wxx, W0t is 0, W3t is 0. All of these is exactly the same situation we had in the previous case when we solved the heat equation there, right? When we had the initial condition something with the two conditions as 0 so that we can use the separation of variables. Okay? So we did in the last class, the separation of variables method to solve this, right? And another great thing is that we didn't require much for V. We just need to find something that would satisfy the heat equation, and it would satisfy this and this. Okay? And we now operate in the same principle that we have been operating so far. We don't solve differential equations, do we? What do? We make educated guesses, right? We just make guesses, and if it works, and we do manage to get the solution, then we're done. Okay, it works. Okay. All right. So how does it work? Start with some V. So this is our main idea. Let's try this. So I want something that's 0 on this. So V has to be something that's 0 here and 20 there. What kind of function can give you that? 0 at 0, 20 there. Give me a function that will do exactly that at 3.
AX.
Just AX, right? V of x equals to AX. That's a good choice, right? So I want V of 3 to be 20, so that A times 3 must be 20, so A must be 20 over 3. So we have V of x as 20 over 3x. Oh, but we need a function of t, but we don't care. We just have a function of x only. Now the next question is, does this really satisfy the heat equation? What do you get if you do Vt?
0.
You get 0 because it doesn't have any t. If you differentiate by t, it's going to give you 0, right? Okay. All right. What do you get if you differentiate by x?
20 over 3.
20 over 3. What do you get if you differentiate twice?
0.
So is it true that Vt is equal to 4 times Vxx?
It's true.
Yeah, this is 0 and this is 0 as well. And 0, last time I checked, 0 is equal to 0. Right? So done. We found a solution that satisfies the desired conditions. Okay? And therefore, we can now express W as that. However, there's one more thing. I forgot to talk about the initial condition of W. So tell me what W of x0 must be.
0.
No.
Oh, wait. X.
Remember, this is U of x0 minus V of x0, right? That's what we have. This requirement means W is U minus V, right? So if you evaluate W at x comma 0, you better get Ux0 minus Vx0. But what is Ux0? 0. That's what's given there. What's Vx0? No, V is this one, right? So what is it?
Negative 20 over 3.
Okay. So we're almost done. Okay. So we just have to figure out this one. So I need to solve this heat equation with the two boundary conditions with this initial condition. Yes?
I thought that was V of xt. Like, why is it the same as a V of x0?
Okay, so if you have Vxt equals to 20 over 3x, what is V of 1, 1?
It'll be 20 over 3.
Yeah. What did you do?
So
You
it's
plugged in 1 into x, right? Where do you plug in this one?
like
You don't,
t
because
from-
there's no t, right? If I do 1, 4, what do you get? The same thing,
Yeah.
right? If you plug in 0, what do you get?
you get the same.
Still the same thing, right? What's V of x0 then?
V of x0 will be
20 over 3t,
Yeah.
3x. Yeah. So it doesn't change.
okay.
So it's like if you have a constant function, it doesn't matter what you plug into x, it's always the same thing, right? Yeah. Do you have any other questions? So we know that the initial condition here is that minus 20 over 3x. That's what we have. Okay. Now, we're now going to assume that you know that we have an exam tomorrow, right? So you know how to solve for W pretty well, right? Yeah, hopefully. Or you're gonna pull an all-nighter, all right? Okay, I don't know what your plan is, but you should know this, that if you set W as x, x, t, t, and apply the heat equation, that's going to give you x of x, t prime of t equals 4 times x of x, x double prime, t of t. Divide both sides by 4xt. And then x cancels, t cancels, and you end up with saying that, on the left side you have a function of t, on the right side you have a function of x only. Therefore, the only way that you can have a function of t equal to a function of x is if this is equal to a number, and we call that number as negative lambda.
How come you didn't bring the 4 down on the other side?
What did I say? Oh, 4 cancels. Okay, and then we come up with 2 equations. This one means you have t prime of t equals to negative 4 t of t. The second one gives you an x double prime of x equals to negative lambda of x of x. This one has a simple solution. This is t of t, there's a lambda there, equals to e to the negative 4 lambda t. And last time I explained how to get this by using the characteristic equation, but there's an even shorter answer. Just think of this. Differentiate this, what do you get? You get negative 4t coming out, right? So of course it's going to satisfy this. Do you agree? If you differentiate this and put it in here, it'll be exactly the same thing as this itself times negative 4 lambda, because negative 4 lambda gets created by differentiating. If you get it, then you can see that easily that this is the solution. Right? Now this one's not so easy because first you have to write this as x double prime plus lambda x equals to 0. And then we also have to assume that I deleted the boundary condition for w, but you know w of 0t and w of 3t, they were both 0, right? These are all equal to 0. I erased it. So that means x of 0, t of t, equals to x of 3, t of t equals to 0. And we don't want t of t equals to 0 because, or else u is 0. You get a trivial solution. We don't like trivial solutions. Okay? We want all non-trivial solutions. So that forces you to have x of 0 equals to 0, x of 3 equals to 0. And this one here, together with this, gives you a Sturm Liouville problem whose solution, we either did this for homework or for the practice exam. I can't remember, but you'll see that this will have a solution x of x equals to sine of n pi over 3x, with lambda being n squared pi squared over 9, with n equals to 1, 2, 3, and so forth. Okay. So this was called the eigenvalue and eigenvector problem. Not eigenvector, eigenfunction. Eigenfunction. This is an eigenfunction. Actually, any non-zero constant should also work, but we just need to find one of them. So we just choose C to be 1. So that's what we do. So we get that one. Let's just leave vxt equals to 20 over 3x, and then remember u is v plus w. Okay. So we get that, and then putting these together, since e is this and x is this, oh, I forgot that there can be any constant there as well. So if you multiply them, you end up saying that a non-trivial solution that's of the form a function of x times function of t must look like uxt equals to some constant times e to the negative 4 times n squared pi squared over 9t sine n pi over 3x. And then, oh, it's not u, it's w. And then we worked so hard so that the boundary conditions for w is linear, so that if you have these building blocks, you're allowed to just add them up from n equals to 1 through infinity, because n starts from 1. There's the other case when you have the Neumann boundary condition, n starts from 0, and then you actually have a constant term added to it. But here it's not the case. So that's the general solution. And now we have to match it with this one. So I need when t is set to 0, I need the left side to equal to negative 20 over 3x equals to summation, this should be n from 1 through infinity of Cn. E to the 0th power is 1, so you just get sine of n pi over 3x, which calls for a sine series, Fourier sine series. Okay, so this requires Fourier sine series. And then Fourier sine series will give you, let's see, Cn will actually be Bn equals to 2 over L, integral from 0 to L, f of x sine n pi over Lx dx. And for our case, the length of the rod is 3, so we replace this formula by 3. And the f of x is negative 20 over 3x, so we replace that as negative 20 over 3x. And then we perform the integral by any method that you prefer. I prefer the tabular method, so plus minus d integral negative 20 over 3x sine of n pi over 3x. Differentiating gives you negative 20 over 3. Differentiating again gives you 0, so you stop here. Oh, and here's something I found that some of you are still confused about. When you integrate, the reciprocal of this number comes in front. If you differentiate, this number comes out as it is, but when you integrate, you have to take the reciprocal. So it's 3 over n pi, and sine integrates to negative cosine n pi over 3x. Integrating again brings out another 3 over n pi, so it's 9 over n squared pi squared sine n pi over 3x, and the sign alternates plus minus, so plus times negative, 3 and 3 cancel, so you end up with the integral of 20 over n pi. Don't forget the 2/3 in front. Okay. 20 over n pi x cosine n pi over 3x. Then minus will be minus. 9 over 3 is 3. 3 times 20 is 60, so it's minus 60 over n squared pi squared sine n pi over 3x. And you plug in 3 and 0. Okay. Now when you plug in 3 and 3 cancels, 2 times 20 is 40, so you get 40 over n pi. And cosine n pi is negative 1 to the nth power. Cosine of n pi is negative 1 to the nth power. By the way, I've noticed that some of you are writing this without the parentheses. That's wrong. Okay? If you don't have this parenthesis, that's wrong. Okay? Because negative 1 to the nth power simply means negative of 1 to the nth power, which means just negative 1. So don't do that. Okay? Please write down parentheses around it. It's important. Okay, so this is going to turn into negative 1 to the nth power. And sine n pi is 0, so that goes away. And when you plug in 0, both of them gives you 0, so that's the only thing that you end up with. Okay? So you get 40 over n pi, negative 1 to the nth power. And that's your Bn, which is equal to Cn. So you end up with this value for Cn. And then finally, well, not finally, almost finally, we see that W of xt is equal to summation n from 1 through infinity of 40 over n pi, negative 1 to the nth power, e to the negative 4 times n squared pi squared over 9 t sine n pi over 3x. Okay, so I went a little bit faster because I'm assuming that a lot of you reviewed the previous materials, given that tomorrow's the exam. Yes, you have a
Where
question?
did you get 60 from?
60? This 60? This one here? Yeah, so that's 20 over 3 times 9 is,
Professor?
yes.
For the evaluation of integral, I thought I thought there will be minus 1 term.
Oh, no, because when you plug in 0, there's an x here.
Oh, yes.
So when you plug in 0, that goes away. So,
yeah,
so
that's true.
when you plug in 0, nothing comes up.
Yeah, that's true.
So that's what you get as wxt. But we're not done yet, right? We need to find uxt. So what is uxt then?
20 over 3x plus W of x.
So that's the answer. Okay. So other than having to take this separate, figuring this out separately, otherwise it's the rest is same as the 0 case. So it's not that bad. Okay. Now in this next step, I'm going to be even more ambitious. By the way, let me just copy this on a board where it's not captured on the camera because I want to draw this later today if I have time. Hopefully I have time. N equals to 1 to infinity, 40 over n pi, equals to the power e to the negative 4, n squared pi squared over 90, sine n pi over 3x. So, this time, I'm going to make it even harder. Looks very hard, right? Suddenly it becomes a lot harder than before. So what's happening here? What's happening in this case? This is the temperature at the right endpoint of the bar, right? And it's a function of T. What does that mean?
The right endpoint, its temperature is proportional to time elapsed.
So this one-dimensional bar is insulated all across. The left side is still touching ice to keep it at 0 degrees Celsius. But the right side, I don't know what it is, but it's something is heating it up. So that at any time t, it's something is heating it up so that the temperature rises up with respect to time. So time t equals to 1 is 1 degrees. Time t equals to 10 is now 10 degrees. And so on and so on. It just goes up. It could get hotter than the sun if you wait long enough, right? Okay. And we won't have Earth anymore if that's the case. So it's like non-physical. But let's just say this is what you have. And actually, you could make this physical if you just stop the experiment at some time t. Okay, you could make it work. Okay. All right. So in this case, what should we do? Again, it's the same idea. Right? The idea is to think of u as a sum of some function that would satisfy these three, and another function w, because this satisfies these three, this one ends up satisfying just this, and then this being 0. Okay? So it's the same idea, right? Okay. So I need something that satisfies u of 0 as 0 and u of 3 as t. What's our pick? Again, we don't have any knowledge. We just make guesses and make it work.
Something x to the cube thing.
So before, when we had 0 on the left side and 20 on the right side, we just did 20 over 3x, right? So it's similar. We want something over 3x, but we put t here. How's that? So that when you plug in 0, it'll be 0, right? When you plug in 3, you get t. Right? When you plug in 3 into x, you get t. So this really gives you v of 3t equals to t over 3 times 3 equals to t. Okay, what's bad about this one though?
The initial.
Not initial. We don't care about the initial. We'll figure out the initial later. Initial means this one, okay? Yeah. There's a heat equation, boundary condition, initial. Okay. What's bad about this one? Heat equation. It's not going to satisfy the heat equation. How do you check? Okay, so let's see. If V is really this one, what is Vt? You're doing a partial derivative with respect to t, so what do you get?
X over 3.
Okay, so that's not good, right? Because if I do Vxx, well, if you do Vx, what do you get? You differentiate this by x, you get
T over 3.
t over 3. And you differentiate this again by Vx, what do you get? You get 0. Is 1/3 x same as 4 times Vxx? No, it's not. It's different. So it's not gonna. So this is saying that doesn't satisfy heat equation. Bad. So do we give up? No. What do we do? we make it satisfy the heat equation. So let's see what we're up to here. So Vt is equal to 1/3 x. Therefore, here's what I'm thinking. If I do Vxx, according to this equation, Vxx should be 1/4 times Vt. So that it's going to be 1/4 times 1/3 of x. So it'll be 1/12 of x, right? Okay, that means V of x is what?
Oh.
Okay. Plus some constant. Actually, I'm saying something slightly wrong here. This could be a function of t as well because we were doing anti-partial. However, we're not trying to find all solutions. We're just trying to find one that works. Okay, so we really don't care. Okay, just put some constant. Okay, if it works, it works. Okay, at the end of the day, if we find something that works, it's all good. Right? So we just put plus c, some constant. Okay. Now integrate again, we get let's call this c as just a. Okay. And then we integrate again, we get v as 1/24 x squared plus ax, what is that? 72, and this would be 3 ax plus b. Good? We did another integration. All right. Okay. So I know that if you take this one and differentiate twice and multiply by 4, it's going to give you 1/3 x. Right? And now what we do is, we need this term and this as well. And you know what? Somewhere along the way, a and b could have been some function of t as well. So maybe this could be included there as well. Okay? So here's what I think. I want vxt to be t over 3x plus 1/72x cubed plus ax plus b with some constants a and b. Okay. I find this quite fun, but I guess I'm torturing you guys. I'm sorry. All right. So here, if I differentiate this by t once, what do you get? It's a partial derivative. All of these are considered as constants, so those become 0. T becomes 1, so what do you get? Vt is?
1/3 x.
1/3 x. Now, what do you get if you differentiate twice? Well, if you differentiate once, it's t over 3, but if you differentiate twice by x, this is gone. Right? It's a partial derivative, so that's gone. These will be gone. If you differentiate twice, it will be 6x, right? X cubed differentiates to 3x squared, differentiating again gives you 6x. 1/72 times 6x is what you have. Now multiply by 4. And that really gives you 1/3 x. So indeed, it satisfies the heat equation. We checked. It works. Okay? But we still have some problem. What's still not good about this one? What's still not good about this one? We ended up adding these ax plus b, and we don't know if it satisfies these at all. Okay, so now we have to go back and make those work. So let's see. V of 0t is what? T over 3 times 0 plus 1/72 times 0 cubed plus a times 0 plus b. And I need this to be 0, so that means b is 0. Good? All right. And then what about v of 3t equals to t? So I need 3 to equal to v of 3t. And t over 3 times 3 plus 1 over 72 times 3 cubed plus a times 3. B is 0, so we don't care. Oh, sorry, this should be t. So I need this to work, and if you set it equal, I see that these two are the same, so I can cancel them, and this is what I get. I see that 0 must be 1 over 72 times 3 cubed plus 3a. So that if I divide by 3, a must be negative 1/8.
Okay, how you got 0 on this other one?
Oh, this is t, right?
Mm-hmm.
This is t.
Okay.
So I subtract t both sides.
Okay.
Yes.
Remind us how you got v of xt again?
V of xt, where?
V xt above the
The v of x
Yeah.
equals.
Oh, this one. This one.
Mhm.
I'm just doing trial and error.
Okay.
Yeah, just trying to see anything that would satisfy the heat equation and still manage to get something of that sort. I'm just doing. It's like sculpting, really. Yeah, you just put something in. If it works, good. If it doesn't, you try again. Yeah. Just.
So, Professor?
Yes.
The procedure is like, first, there are two conditions. One is heat equation, the other is the boundary condition.
Right.
So we're just managing to make these two.
Yeah, just trying to figure out what would satisfy both.
Okay, but how did you get the instinct to add up these two equations, the t over 3?
Oh, so I got this one and that one. So the thing is, like, these, when I integrated, I kind of cheated. This is really a function of t, right?
Yeah.
And this is also a function of t.
Yes.
So I'm saying that v should be like that, where this is like a function of t. So it could be, imagine this as like, this one as something plus t over 3 times x. Then this one would be same as that one, right?
Oh, yes.
So our initial one didn't work, but like taking a hint from here, I just said, okay, so that's like the missing piece that I should have. So I put that in there. Okay? But then when I do this, then I see that I messed up the boundary conditions again, so I have to go back and change the boundary conditions.
Okay, I see.
Yeah.
Thank
Okay, so with that, now I have, yes.
I think a should be negative 3 over 8.
Oh, did I make a mistake? Let's see. No, I think it's right. So if I divide both sides by 3, that gives you 0 equals to 1 over 72 times 9
Never mind.
plus a. And this, you get 8, so a is negative 1/8.
Yeah, I forgot there was a 3 next to that.
All right. So once you have that, then we plug in v equal to 0 and a equals negative 1/8. And here's what I have. You have v of xt equals to t over 3x plus 1 over 72x cubed minus 1/8 of x. All right. So we have that as a solution. Now what do? Now we have to figure out what w is. Well, luckily for us, once you have w as u minus v, we know that w will satisfy the given heat equation. It's going to have the nice boundary conditions where it allows us to take linear combinations of solutions. And both are 0, so that's the nice one, right? But we don't know what the initial condition is. Okay, who can tell me the initial condition for this one?
That's like ux0 minus vx0.
Okay, so what's ux0?
0.
0. What's vx0?
That's x0, that's, yeah, that's just 72, 1 over 72.
Right, you're plugging in 0 into t, right? So if you plug in 0 into t, that goes away. And this is what you get. So you end up with minus 1 over 72 x cubed plus 1/8 of x. Okay. So now we have another heat equation problem with the initial condition, and it's almost same as the previous one, right? So let's erase everything so far. Except where we get the v, because later we have to plug that back in. We have to add that. But I know for sure that w xt, and this is the same exact calculation as before. It's from 1 through infinity. Since we didn't really change anything, it's cn e to the negative 4 times n squared pi squared over 9t, and then sine of n pi over 3x. Okay. With the initial condition wx0 equals negative 1 over 72x cubed plus 1/8 of x. So now we see that Cn must be that Bn that's given by the Fourier sine series, which is 2 over 3 integral from 0 to 3 of this function times sine of n pi over 3x dx. Okay, so this is actually quite tricky if you wanted to do it with the classical integration by parts, because you actually have to do integration by parts three times. It's a lot of work. So for this one, you really want to use the tabular. So let's try the tabular. So you have negative 1 over 72x cubed plus 1/8 of x. Differentiate, you get negative 1 over 24x squared plus 1/8. Differentiate again, you get negative 1 over 12, then 0. That's what you get. And then plus minus, plus minus, plus minus. And then here you have to integrate. So sine n pi over 3x minus 3 over n pi cosine n pi over 3x. So I put the reciprocal of this number in front. And sine integrates to negative cosine. Integrate again. Oh, sorry. I messed up. Goes one more, right? Sorry about that. So, okay. And then you get 9 over n squared pi squared, still minus sine n pi over 3x. And then this time it's plus 27 over n cubed pi cubed cosine n pi over 3x. And then integrate again, you get 81 over n to the 4th pi to the 4th minus sine n pi over 3. Okay, now because this is really intimidating, let's be a little more smart about doing the calculation. I know from experience that the sine ones are going to give you 0 anyways, because it will always evaluate to sine n pi or sine of 0. They're always 0, right? So these are going to give you 0. Do you agree? Okay. So we only have to pay attention to the cosine ones. So here's what we're going to do. We're going to get 2 over 3. It's negative times negative. So it's like 3 over n pi of 1 over 72x cubed minus 1 over 8x cosine n pi over 3x. And then the other one is this one. So that's positive times negative times positive. So it's negative. It's negative 1 over 12 times 27 over n cubed pi cubed cosine n pi over 3x. And to this, you're plugging in 3 and 0. All right. Oh, this is so hard. Okay. You know what I'm going to do? I'm going to cancel this 3 with this one and make this as 9. Okay, so let's see. 27 canceled and it becomes 9. Okay. And then when you plug in 3 here, That's 3 over 8. Oh, that gives you 0. Oh, awesome. When 3 goes here, this gives you 0. Okay, check that, okay? And then when 0 goes here, that also gives you 0. Oh, nice, okay? I didn't expect that to happen, but in both cases you get 0, okay? So that's all good. And then, so you end up with 2 times 9, which is negative 18 over 12, times 1 over n cubed pi cubed. And then when you plug in 3, it's cosine n pi, which gives you negative 1 to the nth power. And then when you plug in 0, you get 1, so it's like that. And with this minus, I can switch over, and then 18 over 12 is 3 over 2, so it's 3 over 2 times n cubed pi cubed of 1 minus negative 1 to the nth power. All right, now that was really hard, but I managed to do it. So this one is your Bn, okay? And therefore, you see that W must be Wxt. So these are your Cn, so all I have to do is now replace this Cn by what I just got. So this is going to be summation from n through n equals to 1 through infinity of this thing, 3 over 2n cubed pi cubed, 1 minus negative 1 to the nth power. And then you have e to the negative 4 times n squared pi squared over 9t sine of n pi over 3x. Okay, and now that I have u as, because u is v plus w and I have both, now I can write down the final solution. So final answer would be uxt equals to t over 3x plus 1 over 72x cubed minus 1/8 of x. Okay, and then plus summation n equals to 1 through infinity of 3 over 2n cubed pi cubed 1 minus negative 1 to the nth power e to the negative 4 times n squared pi squared over 9t sine n pi over 3x. I guess I need to write this better. Okay, so that's it. That's the solution to this given thing. Okay. Oh, any questions? It was a bit too much, right? Now, there could be some easier ones that looks like this, by the way. Or on the exam, there are many ways I can put this on the exam. Like, I might actually give you the explicit value of vxt, and part 1 could be, given this, show that this satisfies this, this, this. Okay? And then I can ask you to start with the later one. And I can even make this a lot easier by putting ux0 as 1 over 72x cubed. So that when you subtract it, you just get negative 1/8 x. So there could be, so right now, you might think, oh, that's going to be too hard for an exam. I can very much change this in a format that's doable in the exam. So you really need, not for tomorrow's exam. Tomorrow's exam, we're only going by the practice exam solutions I sent out. You guys all check your emails, right? Yeah, so like 2 days ago, I sent out the practice exam solutions. Yes?
How many questions is on the exam?
It's basically the same format. Yeah.
All those questions?
So you can see that at some point I have 6A and 6B, right? One of those will be appearing, and same for the other ones. Like you have like 5A and 5B, those one of them will appear, and then 4A, 4B will. But it will be like all part of a big problem, so that if you mess up one of them, then you mess up the entire exam. Yeah, it's pretty bad. Yeah, I'm hardcore. Yeah. Yeah. Okay, but for the second exam, be prepared to do something like this. Okay. Yeah. So it's gonna be even harder. Okay. Okay, I really want to show you a computer simulation of this one, so I'm going to start something else, but I might not be able to finish that one. So this next topic is wave equations solved with separation of variables. So let's think about following u pt equals to, say, 16 u xx. And the boundary conditions are let's just put pi t. Just to make things slightly easier, because unfortunately, I want to do something that's I want that. Okay, let me just do this one. U of x0 is equal to x times pi minus x. And then ut of x0 equals to 0. So this is a wave equation where you have a string of length pi. And I'm just using pi so that when I do integration by parts, the numbers are slightly easier. So it's 0 to pi, and this condition right here, the boundary conditions are saying that the endpoints are fixed. And this wave equation describes the movement of a vibrating string. It's going up and down. Let's look at the initial condition. If you plug in 0 into this initial condition, x equal to 0, what do you get? 0. If you plug in pi into this equation, you get 0 again. How about if you plug in pi over 2, what would you get? Pi over 2, pi minus pi over 2, that's again pi over 2. You get pi squared over 4. And what's pi squared is about 9, 9 over 4, that's about 2 point something. Yes?
Well, would that be 0 if it's x equals 0? Like, well...
I mean, if you plug in 0 into x, you get 0 times something.
Okay,
so
I thought it was
yeah.
a function.
No. I'm saying that, think of this as a function of x. If you plug in x equal to 0, you get 0. If you plug in x equal to pi, you get 0.
Okay.
And it's a parabola that's upside down parabola. And the highest point is at the middle, which is pi squared over. So it's like, it's something like pi squared over 4, which is about 2. So it's a parabola that looks like that. So that's the initial condition. Okay? And the initial velocity is 0. So it's like you're pulling the string this way, and then you're releasing it. Okay? And then what's going to happen? It's going to go vibrate up and down. Right? So that's what we're trying to find. So this is pi x minus x squared. Okay, so now let's apply the separation of variables. Step 1, set u xt as some function of x times some function of t, so that if you plug it into utt equals to 16 uxx, that becomes x t double prime of t. And then equals to 16 times x double prime of x t of t. Divide both sides by 16xt. And that gives you, well, x divided by x will be gone. So on the left side, you're just going to have t double prime t over 16t of t equals to t and t will cancel, 16 will cancel, and you're going to end up with x double prime of x over x of x. And you again see that this is a function of t, and this is a function of x. When can a function of t be equal to a function of x?
Constant.
When it's a constant function, when no t or x are present. If any t or x are present on this, so if you say this is equal to something, if any x or t are present here, that's going to contradict one of them. If t is present here, then it's going to contradict this case, right? If x is present here, then it's going to contradict it here, because it says, this one says there's no x. This one says there's no t. If there's no x, there's no t, it must be a constant. Yeah. So that's the crucial core argument of separation of variables method. And by convention, we always name that constant as negative lambda, just because if you do that, the second equation gives you the Sturm Liouville problem. Okay? So we're going to do that. This now splits into two equations. T double prime of t equals to negative lambda times 16 t of t. Oh, but this time it's not simply e to the negative lambda times 16 because this is a second derivative, so we actually have to solve this. So what is this in general? It's t double prime plus 16 lambda t equals to 0. If you plug in e to the rx in here, rt here, that's our guess, right? That's our, you know, when you have a differential equation and you're making guesses and you're trying to solve them by guessing, it even has a name. It's called ansatz. It's does anyone speak German here? Nobody? Okay. Well, so I can just say anything, you guys will believe me, right? Okay. All right, so ansatz means a sentence. Okay, so it's like something, a form that should give you a solution. Okay, so you plug this in, and you see that when you differentiate this twice, r comes down twice, so you get r squared. And then when you plug in here, there's no derivative, so r doesn't come down, so you end up with 16 lambda times e to the rx, rt equals to 0. But this is an exponential function is never a 0, so cancel that. And you end up saying that r must be plus or minus negative 16 lambda square root, which is plus or minus 4 times square root of lambda I. So that your t of t must be e to the 4 square root of lambda it, and then there's the minus 1. If you have that, then it gives you the cosine 4 square root of lambda t plus I times sine 4 square root of lambda t. And then this is not what we prefer, because why don't we like this solution? This is a real world problem, right? Yeah. Do we like this solution?
No.
Why not? Because there's an I there, right? So what do? So we observe that taking the real part and taking the imaginary part separately, plugging in here, you'll see that they're separately solutions. So we get these solutions, and we say t of t must be c1 times cosine 4 square root of lambda t plus c2 sine 4 square root of lambda t. Okay. All right, so we get that. And then for the x part, we get the same kind of equations. X double prime equals to negative lambda x if you just simply multiply x to the other side. Move this to the left, you get x double prime plus lambda x equals to 0. And on top of that, these conditions, u of 0 t equals to u of pi t equals to 0 means that x of 0 t of t and x of pi t of t should equal to 0. But since t of t is non-zero, we don't want this to be 0 because if that is so, then u just becomes a trivial solution, and we're looking for non-trivial solutions, right? So we use that to say that x of 0 and x of pi, these are both equal to 0. Okay, so this one, along with this, gives you the Sturm Liouville. And although this is something that we haven't done, this Sturm Liouville, I can just write down the solution. Sturm Liouville will have the solutions. Well, guess what? It's a function that gives you 0 at the endpoints. What would that be? Is it sine or cosine? Sine goes like that, right? Cosine goes like this, right? So which one has 0 at the endpoints? Sine, right? So we know it's going to be the sine. And it usually looks like sine of n pi over Lx, right? And for us, L is pi, so it's going to be this one. So that this cancels. So you're going to get sine of n pi, nx, sorry, sine of nx, with n being 1, 2, 3, and so on and so on. And if that's the case, lambda will become, you differentiate this twice, right, to get the lambda value. If you plug this into here and here, where you get to differentiate this twice, n squared will appear. And that has to cancel with this one, so you see that lambda must be n squared. Is this okay, or should we actually? Okay. Well, after this, if I do have time, I'll try to show you. But I don't think we're going to have time. But, okay. So that's one you have, and then so we're actually done with step 1 because now you see that uxt must be some constant times cosine 4 square root lambda t times sine of nx plus c2 times sine 4 square root of lambda t sine nx. Now this is a bit more confusing than the heat equation because you end up with 2 constants, right? And the reason is it's 2 derivatives in t, and that's actually why we needed 2 initial conditions. If you have 2 derivatives in t, you better have 2 initial conditions. Now we never do triple derivatives in t, but if you had 3 t derivatives, then you better have another initial condition, 3 of them, okay? And so on and so on, okay? So that it's going. Each of these will account for those separately. Okay. So these are the building blocks. Once you have the building blocks, what do? How do you find the general solution? General solution is. What do you think? Sum, yeah, you add them up, right? So let's do this. Since I don't like C1 and C2, let's just put A and B. Okay. So we're going to say uxt is equal to summation of n equals to 1 through infinity of capital A, because I also want to use capital because it's going to confuse with the Fourier series A and B, so I'm just going to use capital AN cosine, square root of that lambda will be n, right? So this is going to be cosine of 4nt sine nx plus bn sine 4nt cosine nx. Okay, so that's the general solution. Of these three, which one we still haven't managed to make work? This. Which one did we not make work yet? The initial condition. We never have done anything to it. So now we have to work on that one, okay? So let's plug in ux0, and you'll immediately see why I said there's one for each of the conditions. If you plug in t equals to 0, what happens to this one? The bn ones. Becomes 0. Sine of 0 is 0, right? So ux0 will just give you summation of n equals to 1 through infinity of the an, and cosine 0 is 1, so this is sine nx. And since this is pi x minus x squared, you're really looking at an to be the Fourier sine series coefficients. Then you're going to get that. So I really needed to put this as capital A because it's going to confuse with lowercase a. So this is really lowercase bn. Right? On the other hand, if you differentiate this and then you plug in 0, okay, that's a little tough to do, but if you differentiate this, you get sine, right? Sine of something. And when you plug in t equals to 0, what would you get? If you differentiate cosine, you get negative sine, and you plug in 0, you get 0. Sine of 0 is 0, so that's going to go away, right? This one, when you differentiate, you get 4n bn, okay? And then you get cosine of 0, so that's going to be 1, and you get sine of nx. Now, because this one is 0, you're really asking what is the Fourier sine series of 0? What's the Fourier sine series of 0? If you have 0 for every one of these, it will be 0, right? So for this one, you just get bn equals to 0 divided by 4n, which is a 0. Okay. In general, you'll have to find the Fourier series and divide by 4n to get the other one. Okay. All right. So now we're still working. We just have a little bit more to go. So we have, let's see. I should start with bn. So bn equals to 2 over pi, 0 to pi, of pi x minus x squared sine nx dx. So that's going to be our bn, which is same as capital AN. So let's do the tabular. Plus minus d integral pi x minus x squared differentiates to pi minus 2x, differentiates to negative 2, differentiates to 0, sine nx, negative 1 over n cosine nx, negative 1 over n squared sine nx, positive 1 over n cubed cosine nx, plus, minus. And once again, if these are polynomials, by the way, this trick only works for polynomials. Don't use it when it's not. For polynomials, we know that these sign terms will give you 0. So we just have to calculate 2 over pi x minus x squared. And actually this is x times pi minus x times negative 1 over n squared, no, negative 1 over n cosine nx. And then this one, minus 2, 1 over n cubed cosine nx. And you have to plug in pi and 0. When you plug in pi here, it's going to give you 0 because pi minus x. When you plug in 0 here, it will give you 0 because of x. So this one will create nothing here. So you just have to plug pi and 0 here. When you plug in pi, you get, let's see, 2 times negative 2 is negative 4 over n cubed pi of negative 1 to the nth power if you plug in pi. And then when you plug in 0, it's 1, so you have to subtract. Which, you can leave it like this, or you can switch around consuming that minus. It doesn't matter. But that's your an. Your an. Okay, so we can now write down the full solution. The full solution is u xt equals to this plus this, but we already found out that dn is 0, so it must be summation of n equals to 1 through infinity of negative 4 over n cubed pi, negative 1 to the nth power minus 1, and then cosine 4nt sine nx. So that's it. Alright, so now give me a moment, because I always have trouble figuring out how to work this out. You have like 30 minutes, and I want to show you how to draw graphs of the heat equation. It's kind of cool.
You're writing the code right now?
Huh?
You're writing the code right now?
Yeah. So let's first write down what that is. U xt equals 20 over 3x plus sum from n equals to 1 through infinity of 40 divided by n pi of negative 1 to the nth power e to the power of negative 4 times n squared pi squared over 9 t sine of okay. Let's make this okay, so here's what we want. We earlier in today's class we solved the heat equation where left end point was 0, right end point was 20, initial condition was 0, and then we ended up with this solution. And we actually want to see if indeed this gives you the correct solution according to our intuition. Okay? Whether this does give us the right graph that we think it should be. Okay? So here's what we want to do. You can go to Google Colab. You can just Google Colab. And this is an online version of Python. It's very handy because all the packages are mostly installed. And the one that I like to use is PyLab. So from PyLab, import star. Maybe I should make this bigger. Okay, so that's what I do. And then if I shift enter, it will import PyLab. And what it does, it gives you all the math functions that we want and the graphing capabilities as well. Okay? All right. So here's what I want to do. So I want to say t equals to 0.0. Okay. And then I'll have to fix my domain. I want to use linear space of. So the interval I'm working with is this was 0 to 3, right? So 0 to 3, and I also have to tell how many sample points I want, because the continuum doesn't exist for computers. You have to tell how many points that you want to divide this by. So I'm going to divide it by 301 points, so that each will be like 0.1, something like this, right? If I ask what x is, it's going to tell me all this. Okay, that's x. Okay? All the values from 0 to 3, increments of 0.01. Okay? All right, so now I'm going to say y, or the value of u is equal to 20 times t divided by 3 plus gee, it's like, oh, is there a sum function? Oh, there's sum. Oh, it does. I don't like it. All right, well, let's do a for loop. Okay, so I'll just say u is equal to 0. Actually, I'll just say 20 times t divided by 3, okay? And then I'm going to do a for loop. And who knows what for loops do? Anyone? Coding?
Kind of forgot.
Okay. All right. I thought some of you might want to be a data scientist. No? Nobody wants to do that? It's really hard.
I'm only taking my first coding class.
Okay.
Same.
All right. So for n in range, 1 through, let's say we had 200 times. Okay.
Oh, so
This actually adds up to 199, but you don't have to know that. Okay. Then what I'm going to do is I'm going to say u. I'm going to add to u because it's a summation of what was our function? I forgot. It's 40 over n pi negative 1 to the nth power. Right? So let's go back. 40 divided by n times pi, and then you multiply this by negative 1 to the nth power, negative 1 to the nth power. In Python, you have to do 2 star to take the nth power, and then times exponential function of negative 4 times n squared times pi squared,
Divided by 9.
Times t divided by 9.
Yeah.
Then times sine of n times pi
divided by
times x divided by 3.
Yeah.
Okay. And you do this, and then I execute this. Okay. And then let's plot this. Plot x comma u. Okay.
So that's one dimension. That's 2 dimensional.
No, something's not right. Oh, I forgot to put t times x. Right? Yeah, t
Yeah.
times x. That should have been. This should have been t times x. X times. No. This doesn't have t there. Sorry. What happened? Oh, it's x times 3. Oh, sorry. Okay, sorry about that. So let me run this again. Okay, so what happens is that initially it's 0 everywhere, and the right end point is 20. And now you see this wiggles here. That's called Gibbs phenomena. Whenever you have a sudden jump, then the Fourier series hates it because it's trying to approximate a jump function by using sines and cosines, which are continuous functions. So we talked about how when there's a jump, the Fourier series converges to half of the jump, right? But in reality, if you truncate it, it actually does some wild things before going to that next jump. So that's called Gibbs phenomena. And I talked about how Fourier series gives you all these conveniences of JPG, MP3. But whenever you have a sound wave file that has like a huge jump, like think of a rock and roll, heavy metal that has like a very big snare and it's like it's really loud and there's a sudden jump, then it gives you poor approximation. So for rock music, you really need to have a high quality bit rate in order to get a good sound. Whereas for classic, it doesn't have this much, so it's okay. But that's a side issue. But let's try to change this again. So let's see. Let's just put this in the same line here. And let's see what happens if I have t equals to 0.01, just like split second after. And after that, I'm going to plot it, x comma u. That's what we get.
Oh, that's more clearer.
So this is exactly what we thought about, right? So like a split second later, because the right side is kept at 20, the right side temperature will go up, whereas the left side is still 0. So, and it takes a while for the heat to actually propagate to the left side, right? So that's what you get. Now let's make the time bigger. Let's say 0.02. Let's try to draw that. And I guess it's not very clear. What if I do 0.1? Now you see that the heat has propagated more to the left side, right? And then if I have like 1 second later, and this is almost like a straight line. Already it's hard to distinguish between a straight line. And then 0.4 or something like that will be slightly bent. So eventually when time t goes to infinity, you get a straight line from 0 to 20. That's what we mean.
Professor?
Yes.
In this one, what did you plot? In this smooth graph, what did you
So
plot?
in this smooth graph, I plotted this with the value of t being 0.04. 0.4, sorry, 0.4. So it's a graph of x, right? If you give a value of t, you end up with a graph of x. And if you graph it, this is what you get.
How about the wiggles, the wiggling?
So the wiggling only happens at t equal to 0. The moment you go slightly, then the wiggle disappears, right?
Oh, I see.
Like if you put like 0.0001, wiggle almost immediately disappears. And
Because it's a jump and it's
at time t equals to 0, you have a jump because everywhere on the rod is 0, but on the rightmost side, you're letting the value as 20. So there's a sudden jump to 20. That's what's happening.
Okay, so if the points we're taking is too little, then we will observe the wiggle. But if we
Right, right. If this is very small, let's add a few more zeros, then you're still going to observe the wiggles, Gibbs phenomenon.
okay.
So when you apply this to JPG, it's called artifacts. Have you ever tried to use like Photoshop or some graphic software where you save a regular file as a JPG and you select the quality of it? You can make the quality at 70%, which makes the size really small, but you can also increase it to 90-something and the size becomes bigger. If you ever looked at the 70% one, you'll see that at the boundaries of a picture, there's some extra lines that's parallel to it. Those are what's called the artifacts. And those happen because of the Gibbs phenomenon. Okay, so, wow, I thought this was going to take a long time, but it didn't. And that's it. That's all I prepared for today, so I guess that's all. Yeah. So we have an early class. Oh, do you want to see the this one? Sturm Liouville for this one? Should I do that one?
Yeah, sure.
If you have x double prime plus lambda x equal to 0, x of 0 equals to 0, and x of pi equals to 0, then the non-trivial solutions are signs. That's what I want to prove. Okay. So, case 1, see, lambda can either be positive or 0 or negative, right? So we start with the lambda case being positive. For that, the characteristic equation for this becomes r double prime becomes double prime becomes r squared. No prime becomes r to the 0th power, so it's just this. And we have r squared equals to negative lambda. And then r becomes plus or minus square root of lambda I. And then that says e to the square root of lambda I x is a solution, which is cosine square root of lambda x plus I times sine square root of lambda x. So that's the solution. Which is not at all real, so you better have complex. You better take the real parts. So this and this separately becomes a solution, so we know that x of x better be c1 times cosine square root of lambda x plus c2 sine square root of lambda x. And by the way, for tomorrow's exam, I will have something of this sort, or it could be like the one with the primes. But whenever you do these, don't just put the answers down, because I'm not going to give you credit if you do that. You actually have to show all this work, okay? So you have this, and then you apply the boundary condition. So x of 0 equals to c1 cosine of square root of lambda times 0 plus c2 sine square root of lambda times 0. Cosine 0 is 1. X of 0 is 0, so 0 is equal to c1 times 1 plus c2 times sine 0 is 0. So that says c1 must be 0. Now let's see what this gives you. X of pi gives you c1 times, actually c1 is 0, so this is just 0, I don't care. c2 times sine of square root of lambda times pi. So that since x of pi is 0, you have 0 equals to c2 times sine square root of lambda times pi. Now, we know that if two things multiply to 0, then one of them has to be 0, right? So this says either c2 is 0 or sine of square root of lambda times pi equals to 0. Okay. And then you think about this one, and this is something that you must write, okay? So for this one, what happens? X becomes 0 times cosine square root of lambda x plus 0 times sine square root of lambda x, because I have C1 as 0 and C2 as 0 as well, right? Okay. Then we get x as what? What's that?
0.
0. Is that good or bad? Why? Because we're looking for non-trivial solutions. So this is trivial solution. So no good. Okay. So therefore, this must happen. Okay. And for sine functions, if you draw the graph of sine, this is the graph of sine, right? What is this value? What's the x-coordinate of this value? Pi. What's the x-coordinate of this value? What's the x-coordinate of this value? This one? 0. Where? Negative pi. So, what do you observe? When is sine equal to 0?
And pi and solid.
So, sine is 0 when the thing inside is equal to some multiple of pi, some integer multiple of pi, right? And you solve this for lambda, and because lambda is positive, n must be positive as well. So you have lambda equals to, well, if you cancel the pi and square both sides, you get lambda equals to n squared. And because lambda is positive, you better have n equals to 1, 2, 3, and so on and so on. And then you have to do case 2, where lambda is equal to 0. In that case, you have x double prime equals to 0, because lambda is 0. That goes away, and you have x double prime equal to 0. This time, do not use the characteristic equation, because you're going to go to dead end. You just integrate both sides. If you integrate both sides by x, what do you get? X prime as integrating 0 gives you some constant, right? A. You integrate again, you get x equals to ax plus b. Okay? And then you apply the endpoints. So if you plug in x equal to 0, the left side will be 0, and you get a times 0 plus b, so that b must equal to 0. And then if you plug in x equals to pi, then 0 would equal to a times pi. B is already 0, so a must be 0 as well. So if a is 0 and b is 0, what do you get? You get trivial. Now, is there any way out? Is there any way we can get a non-trivial solution in this case? No, you don't have any choice. X has to be 0. Okay? And because of that, since x has to be 0, that means lambda equal to 0 is not an eigenvalue. Okay? And then the third case is lambda negative. What do you do in that case? Don't do it. Okay? Now, if you see other YouTube videos or other books, they will do it. Okay? But I'm just making things easier for you by asking you to skip, because later on in this class, I will show you that there's a reason that the negative values can never be eigenvalues of a Sturm Liouville problem. So I'm going to prove that at some point. Yes?
So on the test for the third case, do we have to
You just say,
show anything,
we
or
don't,
just
you can just skip. That's
just
fine. Okay,
not
yeah,
write
just,
anything for it?
yeah, just don't write. Okay? So putting everything together, oh, well, by the way, when lambda is n squared, then that gives you x of x. C1 is 0, but C2 is non-zero. So C2 times sine, and square root of lambda is n, so you get nx. Okay. So that's going to be your eigenfunction, and this will be your eigenvalue. But see, from all the possible multiples, we just choose one of them. Just put 1 there, okay? It's just like when you find eigenvectors in linear algebra, you don't find all the multiples of eigenvectors, you just find one value, right? So that's what we do. So this is the final answer. Now, let me add a bit more comment. If you have the primes, in that case, you will see that lambda equal to 0 is indeed an eigenvalue. And for that, you have to start your n from 0. Okay? If you start from 1, that will be considered wrong. Okay? So that's what you have to do. Okay? That's all.